Okay, let's do it, peeps. We need to remember a few things before we start, and those things we need to remember are what did we obtain from position, what did we obtain from velocity, because there was a vector loop that we proposed already, and that vector loop was, I'll do my best, you see, I'm going to use the ruler this time for the arrows. Oh, that color is not nice, sorry. This one, and we label that as, let me fix this. Oh no, it's already fixed. R1. Check at this. With this ruler, you can even check that this is actually at minus 60 degrees. You know, that angle is here, right? Here we have, oops, minus 60 degrees. Oops. So it is valid. Let's do the second arrow then. What's wrong? That's the second arrow. We label this as R, what was it? R3, I believe. And finally, that one there. Which was R4. Okay, that comes from the position analysis, and we solve for R3 and R4 actually. So R3 was equal to what, and R4 was equal to what? This should be in your notes already.
R3 is equal to 6.93. R4 is equal to 3.46.
Theta 4 was equal to what? 0, right?
0.
Theta 3, 300.
Yes.
Is that one. Okay, thank you, Gustavo. And then, so this comes from position analysis. We did the velocity, and in velocity we obtain omega 3 and linear velocity v3. Do you remember, sorry, those values? When we consider the input to be before we did say that we were going to take as input, we multiplied by 10 because we wanted to validate against SolidWorks. So the input was given in inches per minute that we then acting at 180 degrees, which means minus 1.66 inches per second. This minus comes from the direction of the velocity. And I have put this in a different color, which means this is data given by the problem. Now keep in mind that in the problem, they are not giving you 100 inches per minute. They are giving you 10. So I'm multiplying everything by 10. Why? Because I want my SolidWorks simulation to be quick. That's the only reason. So what was the solution for omega 3 and B3?
For B3, it was minus 0.83 inches per second. And for omega 3, it was
minus 0.83 inches per second. And omega 3 minus
0.27. 207, yeah.
Radians over second. Okay, this was solved before. You can check the video if you don't remember where this comes from, but it was the velocity solution. Now let's work on all this stuff that I just wrote is for you to remember. Now let's start analyzing acceleration of this thing. Let us remember which type of vectors we have. Okay. So I have R1, R3, and R4. Magnitude orientation. Vector R1 was the one that is fixed, so it's constant for both. R3 is variable for both, and R4 is variable for magnitude and constant orientation. And because of this guy, we are expecting to have the Coriolis component. The velocity vector loop equation was simply B4 equal to B3. You remember? If not, check your notes. You should find this equation here. And in order to analyze this for acceleration, we derive that with respect to time. That means okay. So when I derive that with respect to time, what do I get? I'll simply get two acceleration vectors. Those two acceleration vectors, okay? All good? Okay. Let's see which type of vectors we have here. Acceleration vector A4 will have only component in the horizontal axis. You agree? It comes from vector R4, which acts only horizontally. You can check it here in the diagram. So acceleration will be, and it's a linear acceleration because that type of vector is only changing its magnitude. And that will be equal to the very long vector, right? Why? Because it's variable for both. So everything has to appear in this case. Everything has to appear, which means that I need the very long version of the vectors. We covered, I think it was 1 week ago, the different type of vectors we can have. Okay? And there was one where both magnitude and orientation are changing. And those type of vectors look like the following. Correct me if I miss any term because this is very long. Or if I make a mistake in the signs. You can copy this vector from your table. I think it was Fer Alonso, the one that shared the table with us. Also, Majo sent the table to me, so you can check Slack if you don't have your notes and download the table. I think that's it. So I have the component that has omega squared, alpha, which is the angular acceleration, the linear acceleration, and the Coriolis component, right? All this is just because of that guy here. Okay, now let's check what we know and we don't know. So I don't know. Which things I don't know. So I can check for which variables I need to solve the system of equation. You think I know R3?
Yes.
Now I know it, right? Because I have solved the position. So this I know. Do I know omega 3?
Yes, cost velocity analysis.
Okay, I have passed velocity analysis. What about theta 3? Do I know it? It's given, right? It's 300 degrees. So this I know. I have solved position, so I know that one. What about alpha 3? Do I know it? The angular acceleration of link 3? I don't think I know it. That's probably one of the things I need to work out. This given. What about linear acceleration of link 3? Don't know it. Given. Solving velocity. Given. And that's it. So I have two unknowns. Oh wait, no, what is this? What happened to that guy? What can I do with that guy? Maritza, what can I do with that guy? This A4 here.
I don't know.
Okay, no problem. What can I do with this value here, pips?
You can directly derive from before.
Why do you do?
La derivada de la velocidad 4 que ya tenemos.
But it's constant. This data here, given by the problem, at least if you check the problem, it doesn't say if it is changing with respect to time or not. And if there is no information regarding how the velocity, the input velocity changes, then we assume it is constant. And if the linear acceleration, if the linear velocity is constant, what do you think is going to happen with the linear acceleration?
0.
It doesn't exist, exactly. So I'm going to replace that with 0. Okay, so 0. I'm going to add the note 0 because before is constant. Okay, keep that in your notes. So 0, and I can start splitting this into two components so I can save some time. Horizontally, I have R3, omega 3, right? Square. Cosine of theta 3 square. This is negative. Minus R3 alpha 3 sine of theta 3 plus A3 cosine of theta 3 plus 2 times both of the velocities. And this is minus, right? Because of the sine of theta 3. All that is happening horizontally, and you can start substituting some values already because you have numerical values for most of these things. So you have 0.
Okay.
Yep.
Why do we have cos 3 squared at the beginning? Why is it squared?
Oh no, that's not square. There you go.
Okay.
Thank you, Fer. Okay, if you substitute here, which was the value for R3? 6 point something, right? 6.93, 96, 90 something. Substitute that one there, multiply by the angular velocity, which is 0.207, and multiply by the cosine of theta 3. Do that. This is a number. Give me that number. Use your calculators. If you remember, we need some calculators sometimes. I don't know if Fabiola is calculating with us or is enjoying life.
Both.
Both. She's
I
enjoying
enjoy
life
life
because
doing
she's calculating
calculations.
with us. Okay.
Yeah, that's true.
I got 0.15.
Say that again, please.
I got 0.15.
I got minus 0.149.
Yes.
Okay, thank you, Julio. Now the second term, at least multiply R3 by sine of theta 3. This you're going to leave it because that's a variable you want to calculate. So leave alpha 3. So multiply R3 times the sine of theta 3.
Minus 71.
Say that again.
71.
71. I don't know. Sine of theta 3
Half minus 6.
minus 6.
1.
I think it's positive, right? You have a sign, a minus sign here.
Yes,
the
I
sign,
got 6.
The sign of 300 will be negative, so this multiplication will become positive. And when you multiply the sign of 300 times 6.93, you have 6.001.
Yes.
So it is positive and it's almost, I'll put 6 directly. Okay. Plus 6 times alpha 3. What is the cosine of theta 3?
0.5.
0.583. And finally, this is also a numeric value. Substitute omega 3, which is 0.207. B3 is 0.028 or 029. I don't remember which is the value we wrote. 0.83. Substitute these two values here. Multiply by 2 and by the sign. Check that these two are negative. These two are negative. This is negative and this is negative. So all these will become positive.
I got 0.298.
0.298. So that's one of the equations. From this one, we can work out for A3 and substitute in the second one. So let's check which is the value for A3. It will be minus 0.149 minus 6 alpha 3 over 0.5. Okay. Let's do vertical components. Again, this is equal to 0. And vertically, I have minus R3 omega 3 squared sine of theta 3 plus R3 alpha 3 cosine of theta 3 plus A3 sine of theta 3 plus 2 times B3 omega 3 and the cosine. Substitute numbers, give me the numerical values. This bit here is how much? Multiply it. You have the value for omega, you have the value for theta, and you have the value for R3. So it would be R3 times 0.207 square times the sine of 300. This is 0.258 or 57. Plus cosine of theta 3, which is,
3.4.
this would be 3.46, right? Which is the sine of 300. It's a negative one, is 0.86683 plus whatever this is. So I have 0.23 times 0.07 times 2 times 0.5. Anyone calculated the last one, please?
Yeah, I have 0.171.
0.171.
Yes.
Okay, substitute this one there and work out for alpha 3. This can be further simplified if you want. Minus 0.298 minus 12 alpha 3. Substitute that one. When you substitute that, work out the math, you'll have minus 0.0496 radians over second square. We are talking about acceleration now, which if you transform this into degrees per second square, you'll have minus 2.841 degrees per second square. Now, once you have alpha 3, you can substitute back again into this one and work out for A3. So this one goes back up and you obtain that A3 is equal to 0.297 inches per second square. There you go. Those are the results. Now let's check if it makes sense. Let me go back to the drawing. You know that this guy here, this slider, is allowed to move linearly along link 3, this link that is rotating, and also is allowed to rotate because that link is rotating. So it makes sense that it will have all the components of acceleration. It will have it will have angular acceleration and it will have linear acceleration. Okay? Let me show you something. You know what comes, right? Ya saben lo que sigue. Okay, this is the assembly we created. And we were able to validate velocity last time, if you remember. And this is how it moves. Okay, so I have given an input, but a linear input velocity by adding an input actuator or input linear motor with the linear velocity of 100 inches per minute. So you can check that here. 1.6 inches per second, which is the equivalent of 100 inches per minute. Okay. And also I managed to obtain the angular acceleration alpha 3, which is here. There you go. That's the angular acceleration. And according to our calculations, we obtained that the angular acceleration in degrees per second square of link 3 was what? Check your notes. We just wrote it. Minus what?
2.84.
Minus 2.8. And you can see, well, first we need to check at which second we reach 300 degrees in position, right? Because acceleration and velocity are variables or parameters that are intrinsic to a specific moment in time. So before that, before checking acceleration, let me close this for a second. Let me show you the graph for position. This is omega 3, okay? And I need to check when it reaches. No, this is omega is velocity, so I need theta 3. Theta 3 is here. That's the one. So which angle I'm looking for? I'm looking for 300 degrees or minus 60, right? Both are equivalent. And when do I reach minus 60? Minus 60 should be somewhere between these two. So let's check. I have minus 61 at 5.23 seconds. So minus 58 at 5.02 seconds. Or if you want to be more precise, you can export this and check the Excel file instead of fighting. So I'm going to check the Excel file. Okay. Excel file, I have it here ready for you. Theta 3, which is the Excel file. This is the angular position, desplazamiento angular. And let's check for minus 60 degrees. Minus 60 degrees happens at there you go, 5.16 seconds, or depends on which one you think is closer, or 5.12 seconds is minus 59.6. So it should be somewhere between these 2 seconds. Okay. Then you can check the value for the angular acceleration when it reaches these seconds. You already know that it will happen somewhere between 5.12 or 5.16. So that's alpha 3. This is the file for alpha 3 at 5.12 seconds. Look what I got. Which was the answer in your notes?
2.84.
2.84, and I got, according to SolidWorks, minus 2.8. So not that bad. At least we know that our calculations are roughly or very close to be correct if we assume SolidWorks is the perfect one. Okay? Got it? Makes sense? Works? And in case you want to feel super pro, you can always do better jobs. Like, for instance, this is the second surprise I have for you. I have created this Excel file, it's not Excel file, PDF that includes all the story as pretty as I could. And it has little hearts hidden for you to find a heart in every page. ¿Sí? Para que no te agüites, en cada página encontrarás algún corazón. Ve, siempre hay un corazoncito por ahí perdido. And that's how life is, right? You never know when you'll find another heart. So, ignoring the drama, this is the mechanism. This is the equivalent version in SolidWorks. All this is position. We did that a few weeks ago. Okay, the vector loop, the type of vectors we have, and then the values you told me. We validate position also. Again, SolidWorks, that's easy. We solve for velocity. This is the data given, and we need to remember stuff from position. We obtain the results for velocity. We use those to validate again SolidWorks. We give an input velocity, okay? And we need to check for 300 degrees or minus 60. And we can get that from obtaining the plot between θ3 versus time. And I give a suggestion here. It's a suggestion. It doesn't mean you have to do it, but it says export CSV, replot in MATLAB, because if you use the SolidWorks plot, it doesn't look nice. The axes are very small and it doesn't look very nice. But if you plot it again in SolidWorks, in MATLAB, you can use even Greek letters as variables. You have time, you have θ3, and you check that at which second we reached minus 60. Then we check for that same amount of seconds and check for the velocity, omega-3. Analytically or theoretically, we obtain minus 11.9, and we check that at 5.12 seconds, we have minus 12. So it's not that bad. And it says beautiful. Okay, lo dejan en visto. Next, now let's deal with the acceleration. All these derivative that I explained, stuff that we need to remember. Why do we consider A4 to be equal to 0? Solve for the unknowns, obtain the values, check that against. And you see, MATLAB really makes a difference in the plots. Not that bad. And that's it. I can give you this for you to study, but I'll give you this once you do the assignment. Okay? Because anyway, you can complete the assignment now. This is an example of how you can hand in your assignments. You don't have to do it like that, but it looks cool. And if you include this type of validation, it's even better. But that's only a suggestion. Okay? It's always a suggestion.